And welcome everybody to today's talk will be given by Dr. Quentin Nénon. And let me say a few words about him. I think you did your graduate, you studied in France, right? And then you either you work or study at the Onera in Toulouse, which is an aerospace company. I went to Toulouse a few times when I was working in Germany. So I love the food there, I tell you. Great food. And then people also playing this kind of rugby, right? Rugby, famous for playing rugby in this big square. Yeah. He went to UC Berkeley as a postdoc for a couple of years. I think starting 2018, when he did his PhD, he already specialized in the I would say the radiation belt of Jupiter, and the interaction of the trapped radiation with the moon and the rings. And then he went to Berkeley, working with Andrew Pop, who also gave a talk previously here. And then because it's Andrew Pop, so he worked a lot on the Artemis data on the moon. Yeah, and I think that if you read his paper, and you find that he's very ingenious, in finding all kind of very interesting problem to do to interpret the data. So he's an extremely good data analyst. And now he's back to Toulouse to work at IRAP since January as a CNRS researcher. And I welcome his talk. I think his talk will be very interesting and will be very inspiring for some of us here who are working on Phobos and also the moon. Yes, please go ahead.
Thanks so much for the introduction. First of all, thank you for the invitation. It's an absolute pleasure for me to be here. You can let me know when you want me to stop, and I will conclude. So yes, I'm very glad to talk today about Phobos. So as said during the introduction, very nice introduction, I am now a permanent research scientist in Toulouse, in France. Previously, I was a postdoc at Berkeley, and what I'm going to show today is the work that I conducted at Berkeley with Andrew Pop. On the left, you can see Mars. And at an altitude of only 6,000 kilometers from Mars, we have Phobos orbiting around Mars. It's very close to Mars. And on the right, you can see an actual picture of Phobos taken by Mars Express. Phobos is pretty small, and it is very dark. And today, I'm going to talk about the fact that we have atmospheric escape at Mars. So we have O+, O2+, and CO2+ ions that escape the atmosphere of Mars, and then they impact the surface of Phobos. So I'm going to talk about the characterization of this bombardment by ions, and I'm going to explore the consequences for the modification of the properties of the surface of Phobos. And to better understand these ions that impact the surface of Phobos, we have MAVEN, the NASA MAVEN mission. And this is what I'm going to try to show on the schematic on the left. So you can see the North Pole of Mars, and in purple you can see the orbit of Phobos around Mars. And MAVEN around Mars has a quasi-polar orbit, so if I plot one orbit of MAVEN during one day, it will be a straight line. And what you can see is that the apoapsis of MAVEN was very close to the orbit of Phobos. So it means that MAVEN was crossing the orbit of Phobos once per orbit. And here I show in orange two orbits of MAVEN, just to show that we cover different longitudes along the orbit of Phobos. On the right, I show the longitude around Mars crossed by MAVEN at the altitude of Phobos as a function of time. And so if we take all the measurements accumulated by MAVEN from 2014 to 2019, then we can see that we've crossed each longitude at least 2 or 3 times. So we actually have a good coverage at all longitudes around Mars, so upstream in the solar wind, but also inside the induced magnetosphere of Mars. And what we did is that we put together all these ion measurements collected in situ by MAVEN at the orbit of Phobos in small longitude beams. So this is what I'm going to show today, and really the outline of this talk is trying to better understand the ion environment, to better understand the weathering and the modification of Phobos. So I'm going to get a little back about space weathering in general, the ion environment of Phobos, and then I will talk about results. Can you still hear me online? Just double checking if it works. Hello?
Yes, we can see.
Yeah, no, it's good because after the technical issue, I was wondering. Okay, I'm good to go. So let's talk about space weathering. When you are an LS body, you are exposed to space. So you have variation of the surface due to the space environment. We have four main drivers of what we call weathering, that is modification of the surface. We have the photons, we have the meteoroids, we have the large impactors when you have a big impact, of course, and we have the space plasma, so electrons and ions. And today I'm going to talk about ions of the space plasma and their effect on Phobos. So here I want to introduce some, so not all of them, but some effects of ions on an LS body surface. So you can imagine in orange a given surface. So it can be an actual surface or a small grain. And you have the ion in purple that hits the surface. And so you can have a collision with an atom of the surface. So you displace this atom, so you have atomic displacements, you have recombinations happening inside the material. So you change the properties of the material. What can also happen is that you can actually knock this atom out of the surface with a sufficient energy so that it can actually escape the surface. And this process is known as sputtering. And sputtering is important because when we have ions impacting the surface, we remove some species of the surface easier than others. So basically, we remove a lot of oxygen from the surface, and we leave inside the surface more heavy elements like iron. So we modify the relative atomic concentrations in the surface. And sputtering is also important because it is a key source of material for the exospheres when we want to study the exospheres of LS bodies. And in the end, our favorite ion that impacted the surface, it ends up somewhere inside the surface, and it implements inside the surface an atom that doesn't come from the surface, but that comes from space. That's contamination of the surface. And so we want to understand space weathering at Phobos and at other LS bodies for the fundamental reason is that we don't observe the pristine surface material. And this is this pristine surface material that we want to observe, because this is this material that will tell us, okay, where does this body come from and how does it evolve over time. What we see instead is material that has been modified by the space environment. So when we want to interpret the observations, we need to take into account space weathering. So we have remote observations at different wavelengths. And we do have samples. So it's very nice. The samples return to Earth. And what is nice is that we can analyze these samples in laboratories on Earth. So we have samples from the Moon and from asteroids. For instance, here I show a sample of Ryugu collected by Hayabusa 2. And hopefully, in the future, we will have samples from Phobos back to Earth. So this is a motivation for this work. So I should mention that in 2011, there was an attempt by the Russian Space Agency to collect a sample, but the Phobos Grand mission failed in orbit around Earth. But the Japanese Space Agency, JAXA, is planning to launch in 2024 the Martian Moons Exploration Mission, MMX. And the plan is to collect samples in 2025 and to have the samples back to Earth in 2029. But once again, when we have samples back to Earth, they will have been modified by space weathering and by ion weathering. So we need to understand this ion weathering of Phobos And the first step towards understanding this is to characterize the flux and the properties of the flux of ions that impact the surface. So what are the populations of ions that can impact Phobos? Phobos is actually in a very unique ion environment in the solar system. So we have the solar wind, and what you can see in this sketch is that Phobos is upstream of the bow shock of Mars during half its orbit. So half the time it sees the solar wind. But we can also have ions directly accelerated from the ionosphere of Mars. This acceleration is due to the convective electric field of the solar wind, and this is what we call the ionospheric plume. And when you take into account the distance of Phobos and the typical characteristics of the solar wind, you get that these ions are accelerated to kinetic energies of several kilo-electron-volt. So it's more energetic than the typical solar wind. Downstream of Mars, in what we call the magnetotail, we see very cold ions that seem to escape Mars, and so they should impact Phobos. And last but not least, Mars has a very extended exosphere, that is a neutral exosphere. It is also known as the hot corona. So this is neutral particles, okay. But then in this neutral exosphere, you can get ionization processes, so you get a freshly ionized ion, and these ions then get picked up by the electromagnetic environment, and in the end, impact Phobos. So this is what I call the exospheric pickup ions. So all that to say that we basically have two main sources of ions that can impact Phobos. We have the solar wind, so ions that come ultimately from the sun, and we have Mars, because we have different channels through which these particles can escape Mars and impact Phobos. And the big question is, do the Martian ions play a significant role in the modification of the surface of Phobos when we compare it to the solar wind ions? Okay. So can you still hear me? I guess yes.
Yes.
It seems to work fine. So that was a general introduction. It was just to say the ion environment of Phobos is not totally new. Basically, we know the Martian system. So what we want to know is how much of the flux we actually have. So first we looked at the omnidirectional flux of ions. So when you average over all directions in the sky. And we looked at one very specific process because it was already investigated in the past, and that is sputtering. So is the atmospheric escape of Mars, so with ions coming from Mars, important for Phobos? Actually, this was already discussed in 2014, so before Nénon, by Andrew Poppy and Shannon Curry in this article. The big problem of this paper is that they want to investigate the effect of these planetary heavy ions, but they don't know the distribution of the flux of these ions seen by Phobos. So to solve this problem, they relied on the model. So that's a global MHD and particle tracing model, very advanced model of the Martian environment, to try to constrain the flux at the altitude of Phobos. This is the Martian particle model. So they modeled the O+, and they considered that the O2+ ions should be negligible. Okay, so you take the ion distributions given by this model, and you multiply by what we call the sputtering yield. So the sputtering yield gives you how many atoms from the surface you sputter for each impacting ion. And then you can compute the sputtered flux. So sputtered flux on the y-axis is the flux of neutrals from the surface that are knocked out in space. The x-axis is the position of Phobos around Mars. So at noon, you are upstream of Mars or in the solar wind. Now, what you can see is the effect of the solar wind in red, and the effect, according to this model, of the O+ ions. So what we can see is that when Phobos goes downstream of Mars, so the red arrow here, We turn off the solar wind, and we increase the effect of the planetary ions. And these planetary ions actually dominate the sputtering of Phobos when Phobos is downstream of the red planet. So there is a link here between the atmospheric escape of the planet and the acceleration of its moon. But once again, they had to rely on this model. So can we confirm this with Maven ion measurements? The answer is we're going to see that quickly. So the ion measurements that we have, we have different instruments of Maven, and I'm going to show the measurement of one, which is a very advanced particle detector. It's called the Suprathermal and Thermal Composition Instrument. The PI is James McFadden from Berkeley. So we can observe below 30 keV by 2 ions. We have a large field of view. And we are on this platform here that we can rotate in space. So we can actually cover the entire sky. And we have two main types of data product types, which are very common in space physics. So omnidirectional and directional resolved fluxes. And very importantly, static has a time of flight section, so it is able to identify the mass or charge of the ions. So we can separate what comes from the solar wind, mostly protons and alpha particles, from the eddies that come from Mars. And without any more introduction, here is the result. Here is the flux of ions that impacts Phobos. So here I have averaged over all longitudes along the orbit of Phobos and over 4 years. So this is really what is seen on average by Phobos. The core is the flux, the y-axis is the mass of the ion, and the x-axis is the energy of the ion. So you can see at the mass of 1, we have protons, and the mass of 2, it's likely alpha particles. And we see clearly at 16 and 32, the O plus and O2 plus that come from Mars. So I can go a little bit into more detail. I can split this average as a function of longitude, where Phobos can be. So this is this. So here, the first panel is protons, so only protons. The y-axis is the energy of the protons, and the x-axis is the position of Phobos around Mars. So once again, MSO longitude of 0 degree, we are in the solar wind. 180 degree, we are behind Mars, downstream of Mars in magnetic. So we can see the H plus and H double plus. But what is very unique with this static instrument is the fact that we can observe O plus and O2 plus ions that come from Mars. So here, it is an average of 4 years of the flux of ions that impact the surface of Phobos. So we can see the different sources of ions that I have previously introduced. The solar wind has a kinetic energy of roughly 1 keV. We have this, so when we go in the magnetic field, we have these very cold ions, so low energy. We see this ionospheric plume, in particular in the O2 plus here. And for the O plus ions, you can see another population that we don't see in the O2 plus ions. And these populations are picked ions coming from the extended exosphere of Mars. So it's basically what we expected to see, but what is important is not the fact that we see these different populations, but actually the number, how much of the flux, the fact that we know exactly how much we have for the flux of O plus, O2 plus compared to solar flux. And then we can conclude for this sputtering, so which was investigated before Nénon on the left by Poppy and Trey. Based on the model, once again, it's not based on measurements. So we have this behavior and they say, oh, the O2 plus ions should be negligible. And now we can say after Nénon. So now we rely on actual ion measurements. And the contribution of the solar wind so measured by the instrument is in red. And the contribution of the O plus and O2 plus ions are in green. And so, yes, we find a similar conclusion as proposed by Poppy and Crew in 2014, the fact that we turn off the solar wind in the tail and we increase the importance of the O+ ions. In fact, you can even compare the flux, the values they had in mind were excellent. The only big difference, and this is not only common to this study, but it's common to many studies of Maven, the big surprise of Maven is the fact that we have much more O2+ ions that escape the atmosphere of Mars than what we anticipated. And what we see here with the dashed line is that the contribution of O2+ ions is actually as much as the O+ ions. So if we sum up the two, then we find that the atmosphere of Mars is important for the sputtering of the surface of Phobos. So yes, we can confirm it's a very nice idea that the fact that the surface sputtering of Phobos is linked to Mars. So that's a situation that is unique in the solar system. The Moon around Earth sees a little bit of ion coming from Earth, but not enough to sputter very much from the surface. When you look at the Moon, the gas giants, they are impacted by magnetospheric plasma, but most of this plasma doesn't come from the planet. Here it is really an exchange between the planet and the Moon. Okay. Sounds like I'm still online. So
Yes.
thank you. So this is so we relied on omnidirectional flux. So it means that we compute a kind of average flux that impacts the entire surface of Phobos. We do not resolve how much is the flux on one given position on the surface of Phobos. But actually, we can do that, and this is what we published in Nature Geoscience. If we go for an even more advanced data set, that is directional result of flux measurements. So the fundamental question was, is ion bombardment on the surface of Phobos homogeneous, or is it inhomogeneous? It is motivated by the fact that we can take a sample at a given location, and we want to know how much this would be representative of the entire surface of Phobos. So Phobos is tidally locked. So that's good news for us because it's easy to understand the orientation of Phobos. And the near side of Phobos always points toward Mars, and the far side of Phobos always points away from Mars. So this is Phobos upstream, and when Phobos is downstream, then you can see the near side in blue and the far side in red. Okay, so once again, we take our favorite ions. So the solar wind ions, they travel from the left to the right, and we see less of these solar wind ions when we go downstream of the bull shock. So we expect the solar wind ions to mostly hit Phobos on its far side. The good ion outflows, if they actually flow away from Mars, as I show on this cartoon, then they should impact Phobos mostly on its near side. And the same is true for the ionospheric plume. If it is, as I show here, going away from Mars but not towards Mars, then it will impact Phobos on its near side. So we want to check this, and we want to actually put numbers on this and compute how much asymmetric the bombardment of ions can be on the surface of Phobos. And for that, we have the directional result observations by static. And we have 64 angular sectors in the field of view of the instrument. So we can say how much ions are traveling in one direction or in another direction, towards Mars, away from Mars, towards the North Pole of Phobos, and so on. Yes, so I can hear some noise, but I think you can still hear me okay. So we want to compute the flux of ions that impact each position on the surface of Phobos. So we have two steps. The first step is to determine the anisotropy of the ions. So once again, how much flux do we have in each direction? And for that, we have the in-situ measurements. And then on step two, we're going to assume that each position on the surface of Phobos, shown by this green dot here, is impacted by the 2 pi steradian flux that lies above a local plane. And the result of that will be the first maps of ion bombardment on the surface of Phobos. And it will be based on real measurements by MAVEN, because MAVEN has this fantastic instrument, and it had this very good orbit, crossing the orbit of Phobos once per orbit. Okay, so let's get back to step one. Just to give you an idea of how we did that step by step. So we need to understand the anisotropy, and we want to average the anisotropy over 4 years. So we use a shower directional grid, and we bin each observation of one angular sector in one of the grid cells, so the closest one. So below I show the average from 2015 to 2019. Well, MAVEN is at this longitude range, so we are upstream of Mars, shown by the cartoon on the left. And here I show the flux of 600 eV protons. And the x and y axis are travel direction, longitude, and latitude in MSO coordinates. So what we can see is we have a bunch of ions traveling towards 180 degrees. Basically, this is the solar wind. So the fancy is not only the solar wind, but also look at the Phobos and O+ ions. So here for this one, MAVEN is here, longitude of 85 degrees. And here I show very energetic O2+ ions, 4 kilo-electron-volt. And we see that they travel mostly towards plus 90 degrees. So we see they go from Mars to MAVEN. And the main source of these ions is very likely what I call the ionospheric plume. So direct acceleration of ionospheric ions from Mars to Phobos by the convective electric field of the solar wind. Yeah, there's someone that maybe should be muted online, but otherwise I'm good. Here, last example, low energy O2+ ions when MAVEN is downstream of Mars, so 175 degrees. And what we can see is that these particles, they travel towards plus 180 degrees. So what we can see is that these 140 eV O2+ ions, they travel from Mars to MAVEN or from Mars to Phobos. And this is what I introduced as the cold ion outflow. So this is in very specific position of MAVEN or Phobos or Mars, but we can average over all orbital positions of Phobos or Mars, so all MSO longitudes. And we do a rotation from the MSO coordinates to the local frame of Phobos. So Phobos is tidally locked, so it's pretty easy to do. And we get this map. So this map is in the local frame of Phobos. And the longitude and latitude given here are according to Phobos. So west longitude on Phobos of 0 degrees. It is on the near side and it always points towards Mars. So what can we see? We can see in the middle ions traveling towards 0 degree west longitude of Phobos. Yes, which is actually 180 degree in MSO coordinates. So here I rotated everything, so it's a bit tricky, but if your ion in the local frame of Phobos goes this way, so towards 180 degree, then it would impact Phobos at a position that is at 0 degree. So here, the ions in blue should impact Phobos on the near side, but the ions in the red should impact Phobos on the far side. We can see that the flux of these protons is maximum on the far side. And the two lobes that you can see here are when Phobos goes in the magnetoschist, because we have a thermalization of the solar wind. And I can do is the exact same map, but for 100 eV O2+ ions. And here the story is different. The maximum of flux is not expected to be on the far side, but to be on the near side. And we have almost nothing impacting the far side of Phobos. So then we go to step 2, and we average this, what I call anisotropy map over 2 pi steradian, and we get this. This on the right is what we wanted to compute. It is a surface map, so it is west longitude and latitude, so on Phobos. And for each longitude and latitude, I give the flux of ions that impact this given location. So you can see that 600 eV protons mostly impact Phobos on the far side, and the flux is reduced on the near side. I'm going to go more into details about that. On the left, you can see the same map, but I've just changed the color bar, and I have put an actual map of Phobos behind this colored flux. So you can see that the flux of 600 eV protons is maximum on west longitude of 180 degrees, that is on the far side, but the flux of 200 eV O2 plus ions is maximum on the near side of Phobos. So now we mostly impact Phobos on the far side and the Martian ions mostly on the near side. This is what we expected from my very simple cartoon. But what we can do, and that is unique with Nénon measurements, is to quantify how strong the near side far side asymmetry is. And here it is. Yes, I do have time. Okay. So this is the flux on the y-axis of ions as a function of kinetic energy. So this is what we call a spectrum. And the solid lines give the flux that impact the submass point. So this is on the near side. And the dashed lines are at the anti-mass point, so on the far side. So if we look at the black curves, so protons, at a kinetic energy of roughly 600, 800 eV, we can see that the flux is higher on the far side, so the dashed line, compared to the solid line. But the asymmetry is actually pretty small. It's only a factor of 3. So there is an asymmetry, but it's not that strong. But now, if we look at the purple and red curves, we can see that the flux given by the solid lines on the near side are much stronger than what is seen by the far side. So there is an asymmetry for the Martian ion bombardment that is very strong, up to a factor of 100 difference in the flux. You can also see with the purple lines, the magenta lines, sorry, that the asymmetry is reduced at very high kinetic energies for the O plus ions, and this is due to these ions that come from the extended exosphere of Mars. So clearly, the near side of Phobos is irradiated by Martian ions. So there is a transfer of material from the atmosphere of Mars to the near side, regardless of Phobos. This is the first time it is ever investigated, and we were able to do that in addition with actual measurements. So that was pretty cool. So is it an intense flux that we are talking about here? I can compare with what comes from the Earth and impacts the Moon now. I cannot tell you how much it was in the past because, well, it was in the past, but we can develop models. And the measurements that we have from 2 spacecraft, so Kaguya and Jotan, the flux of ions that impact the Moon should be around 10 to the 4 per square centimeter per second. Okay. The flux of Martian ions that impact the surface of Phobos, so the near side, to be precise, is 10 to the 6. So yes, it is strong. It is at least a factor of 100 above the transfer that we have from the Earth to the Moon. The reason why I'm doing this comparison is because in the Apollo samples that have been brought back to Earth, we see evidence of alteration and contamination by ions that come from the Earth. So if we see that at the Moon, there is no reason why we should not see that at Phobos as well. So the weathering implications of this flux of Martian ions on the near side of Phobos. So we computed again the sputtering and other weathering effect. What we see is that we accelerate weathering on the near side compared to if we did not have these Martian ions. So if you take Phobos with only the solar wind, or Phobos with the solar wind plus the Martian ions accelerate the process. The near side regolith is contaminated by ions coming from the atmosphere of Mars. And this is what I've just said. In the lunar samples, we see terrestrial atoms that have escaped the atmosphere of Earth, including the ancient atmosphere of Earth. So you can imagine when we had dinosaurs on the surface of Earth, some of the dinosaur oxygen ended up trapped in the regolith of the Moon. So it's the first time the contamination of the regolith of Phobos by ion coming from the atmosphere of Mars is considered, and we show that it can be important for the selection of the sampling site of MMX. So yes, we compare with what has been learned at the Moon, and we expect material of the atmosphere of Mars to be preserved inside the near side regolith of Phobos. There is something very ambitious that the community would like to do at the Moon, and so we propose to do it at Phobos as well, is to try to use this archive, the fact that this material is trapped inside the regolith, to try to better understand the past atmosphere of the planet. So the thing about the atmosphere of Mars is that Mars lost its atmosphere, and this is the reason why it's now so dry. But we cannot study this atmosphere anymore because, well, it escaped in space. But some of it remains trapped inside the regolith of Phobos and is waiting for us to be sampled. So this unique link of the atmosphere of Mars, so we did this very simple simulations to show where this O+, oxygen ions coming from O+ and O2+ should be deposited inside the material. So it should be in the top tens of nanometers. What is nice is that you can, in the lab on Earth, you can separate what is shallow and what can come from Mars, and what is, deeper in the material, so it is actually Phobos material, pristine material of Phobos. So I'm going to conclude here. The solar wind ions primarily impact Phobos on its far side. The Martian heavy ions, they mostly impact the near side. And we found that this irradiation of the near side by heavy ions coming from Mars is important to understand the weathering of Phobos. And we have this very cool idea that maybe MX or other space missions can bring back pieces of the ancient atmosphere of Mars to Earth trapped inside the samples. So the blue dot here on the near side and the red dot here on the far side, they have different histories and compositions in the top 10 nanometers because of this escape of ions from the atmosphere of Mars. So yeah, what about the influence of this for when MMX gets to Phobos? Will they decide to land on the near side or on the far side? Well, many scientific motivations will be taken into account, and we hope that the bombardment by Martian atmospheric ions can be important for this section. So this is my very last slide. Basically, key take-away message: Martian ions impact the near side of Phobos. We have this very cool idea on the second bullet point, and fingers crossed for MMX. Thank you very much, and with that, I would take any questions.
Okay, thank you. Thank you so much. Questions from the audience? Okay, yeah, please. Lai, Yanni.
Yeah, this is Yan Lai from National Taiwan Normal University. And I have a question. Just can eject of material the bombardment can change the implantation distribution?
I'm sorry, I did not get everything.
I mean,
can you repeat the question?
The eject of material bombardment on the Phobos can change the distribution of the implementation.
Yes, that's absolutely correct. And so here, what we did is really a first step. The problem is you implant particles, but at the same time you weather the composition. So you implant, you also modify what you already implanted. So the hope is to have a book that we can read in which we could read the past composition of Mars. The true story is that it's going to be very complicated, but at least we should try.
Okay, other questions? Yeah, Xiong, go ahead.
Okay, so good afternoon, Professor. So I have one question. So we know in the moon surface, in the near polar area, so there's a many place we call a cold trap. So there's a cold trap, they will be not receive the solar radiation, become very cold. So there's a cold trap that can be called like the ion. So my question is there any same type of cold trap can appear in the Phobos or the Deimos, this kind of satellite? So if that is possible in the future when we want to send a satellite into the Phobos or Deimos, can we to use this kind of natural cold trap to captures the ion escape from the Mars atmosphere? So this is my question. Thank you.
This is an excellent question. Thank you for your comment. So different pieces of answer for this very good question. Yes, if there is a cold trap, permanently shadowed region on Phobos, that would be nice because it would not be modified by the solar wind. And you're completely right. This shadowed region, even if it doesn't see the solar wind, it could actually accumulate ions coming from Mars because the velocity vector of the ions that come from Mars is completely different from solar wind. Solar wind is basically in the equatorial plane, but the ions from Mars, they can go to, I think I have it here. They can go towards the north and the south. Yes, here. No, not this one. Yes, here. This one, okay. 2+. So we can go to the north pole or south pole of Phobos. And if you have, so you can trap these Martian ions without getting the solar wind impact.
Okay, so my second question is if this Phobos surface that already has a cold trap here, but just like your slide shows, there's a Phobos first one, they are tightly locked, and second one in their orbit inside, they will be walk through the both shock, the solar wind area, and solar wind less area. So my question is because, well, if there's a Phobos, they are walk through this both shock and a solar wind area, will this the ions stay in a space to be flying into this cold trap? So if that is possible, will this kind of ion just like ball impact the ball and to push the cold trap as the ion and escape into the space again? So this is my question. Thank you.
That's very true. You can see this on the map here. In the middle, it is the solar wind. And then you can see these lobes where you can see ions traveling with directions that have higher latitude. So these ions, because of the pole shock and magnetoschist, they have been satellite. So we have more ions traveling to the north and also to the south. We have more, but if you are really at the north or the south of Phobos, you're actually good. This is what I show here on this map on the at plus 90 degree latitude and minus 90 degree latitude, we really are very close to zero. Sure there is a cold trap or a permanently shadowed region at all of Phobos. Would be nice. Or also a large scale one, maybe a global one. No, these are all good comments. I fully agree with all of that. And the complexity captures everything that happens in the Martian system. So it's a really complex system with the bullshit, as you said. Here we were able to work a lot easily because we have measurements. So we don't even try to understand how it works. We just take the data and average. So we were lucky for it.
Okay, so my final question is, so we know the Mars is not only has a one magnetic field, it has a multiple magnetic field. And also we know something type ion that can be retracted and moved by the magnetic this field. So my question is, when there's a Phobos around the Mars, they walk through the different magnetic fields, the area. So will this cold trap inside the ion that will be retract or moved by this magnetic field? So this is my final question. Thank you.
Thank you. What's the mechanism you're talking about? Magnetic fire? Sorry.
It's a magnetic field.
Okay. Yes. Good question. That goes to another fascinating question, but really the one we need to tackle now is, okay, so this is what's happening now by a rate over 4 years. What about extrapolating back in time? For that case, we need to take the past field of Mars. How will this influence? Again, you have the question of when you have the magnetic field of the planet, is it affecting the planet or is it enhancing or increasing the atmospheric escape? You don't understand that at Venus versus Mars. So I think it's another question, but yes, we modify the position of the ball shock, we modify the atmospheric escape, but back in these old days, the solar wind was different, so we have to take into account of that. That's a tricky problem, something we can tackle with balls, but something that should be done.
Okay, thank you. Thank you, Professor.
Okay, let me ask the final question. How about helium? You know, you consider proton, you consider oxygen, and how about helium? Have you considered helium, alpha particles?
Yes. So yeah, sorry. So yes, we take into account the effect of helium for sputtering and the different weathering processes.
Mm-hmm.
So we call it a particle, maybe it's a single charge. It's something with a mass charge of it's this kind that you can see here. For sputtering, and I show here the solar wind effect includes photons and alpha particles. It's important to take into account the alpha particles. Mm-hmm. And for the determination, I show here. You can see the implantation profile inside the depths of the material for O+, O2+, but also for helium blue. Yes, we consider it.
Okay, good. Sorry that, you know, I don't know other people, but from my side, your voice is breaking up, so it's not so clear. Any other questions? If no other questions, I would then close this. Okay, just sorry about that. So Quentin, thank you so much for this very nice detailed talk, and I hope that your result would convince the Japanese to choose the correct sampling site, one on the near side, one on the far side.
I hope so. Or best would be that they collect samples on both sides.
Yeah, right. But otherwise, how can you compare, right?
Yeah, and they can do that. They actually told me that they plan to try to do it, as they did with the Institut at Rubu. That would be very cool. Yeah,
they would do it multiple site sessions, sample return too. Okay, thank you so much, Quentin. I would see you next time. Thank you so much.
Yeah, sorry I got disconnected, but thank you again.